Well, hello, Cal State Straub. Guess what? We're in chapter 12 now. We're going to start lesson 1 of that. As a quick warm up before we get into 12-1's notes, you did an outline of 1 and 2 already and have read this. And if we were in class, we'd be sitting with a partner and making a tea table real quick about what are the similarities and differences between a z-test and a t-test. We've talked about the difference already between a z and a t statistic, the z and the t curve. And now you read what's the difference between the z and the t-test. A lot of them are similar. So jot 3 similarities and 3 differences down into Edpuzzle for me, and then I'll show you a list for you to compare. So, I can find mine. There we go. Here's a list. Maybe you came up with some of these. The similarities, both are used in significance testing, confidence intervals, hypothesis tests, yes. Both curves are symmetrical. Both are used to test the means. There you have to check 3 conditions before you can do either one of them. And they both will have type 1 and type 2 errors. Those are just some thoughts, okay? Differences, we know the t-test uses a degree of freedom, n-1 for mu, and it's only for mu only. The z, the standard deviation, is the population's sigma. That is available, whereas for t it's not. We've talked a lot about the z curve being normal, taller, that normal curve look, whereas the t curve is still mound-shaped but flatter in that middle and more in the tails because there is more variation. We're going to look at that today. The z uses table A, maybe you came up with that, whereas t uses table B. And then, of course, with t, there's no standard deviation of the population known, so we use S. For proportions, you'll always have to use Z. And then this is an interesting one that you may or may not have picked up on when you look at the curve. With the Z curve, you're always going to the left, and with the T curve, it's always going area under the right. So kind of an interesting little difference there. So let's get into the notes. It's going to take 2 days to go through 12-1, but you'll love day 2 tomorrow. The next notes you take will go through all of the calculator commands. So basically, I'm going through all the theory of it today and how to do it by hand, which you need to do first so you understand it. And then tomorrow I'll give you all the calculator commands if you wish to do that instead. So I want to give you a little story. This man right here, William Gossett, he is the reason we have a tea table. He created this. He worked for Guinness Brewery back in Ireland, testing in England. They had their locations back there. He was testing the best variety of barley and hops. It was just very interesting. He was working in a basement, doing all the mathematical calculations for them so that they could beat their competition. So the results varied and the population standard deviation was unknown. So he began to replace sigma with the S in that Z statistic, and they found that they got such inaccurate results. And I'm going to run the applet for you right now just so you can see a little bit of how that worked. Okay. And so he began to increase his Z until he could get the percent confidence that they needed. And that result was the T statistic. What's crazy is this man did this without any calculators, without any computers. And this was basically his life down in the basement with mathematical computations until he could find the right T number that would give them that confidence level with accuracy that was needed. Back in the day, let me see here because I could show you. Here is when he was alive. He died in 1937. So basically, this was the early 1900s he was doing this. And so Guinness did not wish to publish this underneath his name because they didn't want competition to know, where it came from. So it was only allowed to be published as the student's tea table. Okay. If we had been in class, we'd be playing this really, it's kind of fun to do this in a bingo mode, but unfortunately, we're not in class. So hang on a minute. I have the applet up here. We got so many things that we need for today. This applet, I put a link to it in the pacing guide. So if you want to go and do this on your own, we would have been doing this as a class and having a lot of fun shouting out bingo when we didn't capture the true mean. So I'm going to start with this situation. I am starting here with the means with normal curve and using Z with sigma, how we learned in chapter 11, what we've already done. We're going to say the true mean was 100, and here's sigma, and we're just going to take random samples of size 4 for the heck of it. Okay. When we do, oh yeah, I set my confidence level to be a 99%. So you can do the same thing when you get to play with this, but let me show you what starts happening. Okay. We take a sample, and we see when it's green, it means that we've captured the true mean with our sample. And so if we were in class, we'd be going along and just keep hitting enter, 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 enter. And then whenever it came up red, meaning we didn't capture it, then we would have yelled bingo. And as you can see, I'm not able to yell bingo quite yet. If we're doing a 99% confidence interval, then 99 out of 100 times I should get green, right? I need to scroll this up a little bit so I could see there's my percent running right now. I'm at 94. Oops, sample. So I got to 100 of them and I was not able to yell bingo once. I'm sitting at 100% accuracy. You would have expected maybe one of those, or sometime soon I should get a red interval, and I'm just not. Dang. We've already gone. Oh, there it was. I just missed it. I would have yelled bingo on the last one. So I'm at 99.5. Okay. Basically, what this is showing is that with the Z statistic, we are being pretty accurate. We're capturing it. Okay. Well, they didn't have sigma, so they went to using S, the sample. So let me reset this. Okay. And now instead of Z with sigma, we're going to run Z with S, which is what Guinness began to do. Okay. So let's start running samples now with the same 99% confidence level. Oop, there was a red. I would have yelled bingo, bingo. When you're in a classroom, it's pretty funny. You start hearing bingo. Every time I see a red, I got to shout it out. And okay, keep going. Bingo. All right, we're over 100, and as you could see, I had to yell out bingo a lot more, and we're not at that 99% confidence level. We're at 94, and I'm not going to go ad nauseum like we would have in classes of doing a whole bunch just for fun and start shouting it out. But we've lost accuracy. So then Mr. Gossett began to calculate this T statistic. So now let's reset it. And the T statistic will be different for every N value. He had to do it for every single N. That's why you see leaps on the table after he gets to like 40, it jumps to 50 and then to 60, whatever, because the difference was not as significant enough to make a large difference in their calculations between those. Now we have calculators, and of course we'll get the nitty gritties. Okay, so let's run this again. Let's run our confidence interval, and as you can see, we're gaining our accuracy back. Okay. I don't know if you noticed when we were doing this with the sigma with S, that our intervals were also all over the place. Short, long, short. They were changing sizes. As you can see now, we're a little more accurate here. Oops, there was one that just popped in, an incorrect. We didn't capture the mean once. There's twice. Okay. All right, we're over 100, and you could see our accuracy was getting back up there, okay? Still at 98, but if we did this many, 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 many times, it would level out at the 99, but Z with S just did not do that. All right, so I just wanted you to visually see what Mr. Gossett was dealing with when he was let's go from current slide. Okay, when he was doing his work. Okay, so you've got we're not doing the handout. You've got the applet if you wanted to take a further look at that. So let's keep going. So just recall that from your notes that the T statistic looks exactly like the Z, except, oops, this should not say, yeah, this is it right here, S. Instead of sigma, right here it says S, and then we have to remember to use our degree of freedoms when sigma is unknown, okay? Just remember from, we talked about before, if 46 is your degree of freedom and that's not on the table, then you go up the table to the closest one above it, which is 40, the number less than that. Here's what's going to be different now. What we're going to do is we're going to calculate a t value and go figure out where it is, and it will not exactly be on that table. It'll be between two different t values, and then we'll follow that up to get our p value. It could also be on the furthest left or furthest right, so that means it's going off the table either way, and I'll show you how to do that as well. Okay, and then we'll identify the p values as we follow those data values up, and I will show you that today. So let's run a one sample t-test, just like we did a one sample z-test. Okay, but now when you write the procedure, you'll say one sample t because sigma is not known. So it's said that the average resting pulse rate for teenagers is 72 beats per minute. Here's a sample of 20 AP Stat students' pulse rates, and we want to know, is that evidence that it is different than that? Oh, that tells me right now I'm doing a two-tailed test. Okay. Here's the data. So we would have to go put our data into the calculator, run one of our stats, and get X bar and S from it, right? So our parameter population here is a true mean resting heart rate for teens, just like we did before. Ho and ha, just like before. Ho is 72, that's the claim. And then ha is that it's different than that, okay? SRS, we run our three conditions, just like before. This was not an SRS, so proceed with caution. Also, this is less than 30, so you would need to sketch a probability plot. And also in this case, it shows an outlier. So this is a mess. This data is a mess, but we're going to run through it to show you the procedures. Independence probably would map the 10N. Okay, let's keep going. We've run one of our stats, and this is what I got. I got that X bar and that S, plug it into T. Here's where you get your T value, just like we got Z. Now here's where it begins to get a little different. We now have our T. We know that N was 20, so DF is 19. So we're going to use the chart now, the T table chart, not the Z, the T, and we're going to read across degree of freedom to see where this T value lies between. I'm going to pull it up here in a minute and show you. This is one of those odd shapes where T at 0.1067 for degree of freedom of 67 actually goes off the chart. It's not between two, it's off to one of the sides, left side this time. And so when you follow it up to the top, you'll see P is 0.25 and it's greater than that. So I'm again going to interrupt the notes and pull up that T table for you to see what the heck Mrs. Straub is talking about here. Okay, so we had degree of freedom 19, and I look across, here's all the T values, okay? Let me see, what was our T? Our T was 0.1067, okay? So I go across 19, and I see how they're getting bigger and bigger, but 0.1067 would be less than this 0.638 here on the end. Okay, if I had a number, if it had been 1 point something, then I would see that it could fall between two, like for example here, then I would follow them up and I'd see my p-value of between 10 and 15%. Okay, but with a 19, I'm actually going to go off the chart because 0.1 is less than this 0.688. I follow that up and I see the p-value of 0.25. Now, as you see here, your p-values are getting bigger as we go to the left. So if I'm going to the left of this, my p-value is going to be bigger than 0.25. If I have a value that, like I said, that let's say my T had been 1.2 instead. 1.2 would fall right here between these two values. I would follow that up and I would see that P is between, and we always write the smallest to largest. P is between 0.10 and 0.15. Okay. The table only gives us a range of P. It doesn't give us exact. Tomorrow, when I give you the calculator commands, you will get an exact one. Okay. Now, let's just say I had gone off the chart the other direction. Let's say I got a T for DF19 that was larger, was 4. Okay. If I'm going with 4, that's bigger than this. It's not between the last two numbers. I'm greater than this. So I follow this up and I see I'm getting smaller as I go to the right. So my p-value would be less than 0.0005. Okay. So that's how to read the table. Let's come back to our example. If I can, slideshow, sorry, I'm trying to figure this out from current slide, there it is. Okay, so we got our T and our DF, and we need to go see what it's between, and we see that it goes off, and that's what we just were looking at. So we know our P is greater than 0.25, okay? But this is a two-tailed test, so just like Z, we've got to times that by 2. So actually, our p-value for this test is going to be greater than 0.5. That's a really big p-value, isn't it? Super high. So p greater than 0.5, we know that's bigger than 0.05. So we do not have statistically significant evidence, and we're going to fail to reject HO. Okay? So in context, that means there's just really no significant evidence to say that these AP students' pulse rates are different than 72. Now, of course, your conclusion is going to say, however, we had to proceed with caution on SRS and on normality. So if those are not met, this is really not accurate results. You're still going to go sketch. And as you could see, we had a really high p-value. It's greater than 50. For sure, this more than half of your sketch is going to be filled in. Here's your mean from the, oops, sorry about that. What happened here? Let me go back. Okay, sorry. The mean from the claim right here, 72, and then our X bar was 71.75. So we were just 0.25 away. So I went 0.25 away on the other side of it. Okay, it's two-tailed. I did calculate that standard deviation of S divided by square root of N is 2.3-ish. So I went 2.3 on each side. I had a line there, but it got covered up by the shading that I had to try to fit in here just now. So, and then you just put P is greater than 0.25 on each tail, or you could have had above it, P is greater than 0.5 and show the arrows going to both sides. It's very similar to what we've done before. It's just how you find your p-value is now a little bit trickier. Okay. So what I want you to do is see if you can use your table. You need your table in front of you for this. And I want you to tell me what p-value for a two-sided test. So once you find it, you're going to have to multiply it by 2, right? If you had a test statistic T of 2.58 and a sample of 27 people, and I'm going to ask you to put that p-value in Edpuzzle for me, please. Okay, let's see how you did. You should have known that DF is 26. When I go across the table for DF 26, I see that T is between 2.479 and 2.779. On your work, you will show this. You show that you found T between these two numbers. It's very important you write that part down when you're using the table. Okay? And then you say, well, this took me, if I follow those two numbers up to the top, of course, it's reversed. We put the smallest one to the left, but I see that that takes me to between 0.005 and 0.01, but it's two-tailed, so I'll be multiplying those by 2. So I get a final p-value between 0.01 and 0.02, okay? Between 1% and 2%. All right. So I'm just throwing out some basic facts here. Just let's say, is the true mean time different than 12 minutes? So we're looking at the true mean time it takes Mission Vista to evacuate for a fire drill. Well, right now that's going to be really fast, isn't it? Nobody's there. But at any rate, if we were at school and I just said, well, you know, Mr. Walden said, it takes 12 minutes for you guys to evacuate. That's all we're going to interrupt learning. Well, let's test that, okay? I don't think it takes 12 minutes. I did a 2-side testing, just saying it's different than 12, okay? I have a sample size of 15 evacuations and the mean, I've just given you the data there. So that means DF is 14, okay? SRS was not given, and it's not normal. I don't have data to plot. So we've got a lot of proceeds with cautions here. This is just some silly data that I threw out there. But you still go through all the process. Your state, plan, do, conclude, sketch, okay? The do part, it gives us a T of 2.24, okay? What I'd like for you to do right now is go figure out what the P value will be from that T and put it in Edpuzzle. Okay, hopefully you found this T for DF of 14 falls between these two T values. When you follow it up, you get those two P values at the top of the chart. It's two-tailed, so I'm going to times those by 2. So your final answer should be the P value is between 0.04 and 0.05. So if I have a significance test, yes, of alpha 0.05, right there, I know I can reject my HO because P is between 0.04 and 0.05, less than 0.05. It's less than alpha at 0.05. So I have statistically significant evidence to go ahead and reject the HO, saying that the true mean time is probably different than 12 minutes for us to evacuate. Okay? All right. One more thing, you're going to have something called paired t-test. It's not the one sample t, but paired t-test. And this is where you do before and after. Okay? So when you have, for example, you take a test and then you study and then you take the test again. So you're finding this difference between your two tests. You're going to subtract the two figures to find that change or difference. Okay, in the book, there's an example of this if you want to go look at it, and it was about the sweetness of colas. This was kind of gross. They tasted the cola, and they set it aside for a month, and then tasted it again. So it was, how sweet was it a month later, before and after, okay? If it's talking to you in homework, it will about your experimental design for this. Remember, when you do a test like this, you need to assign half the people to do treatment A first and the other half to do treatment B first if they're doing different colas, okay? So oftentimes for a paired t-test, the null hypothesis is that mu is 0, meaning there's no difference. Remember, null means no change, no difference. So the null hypothesis here for paired t is almost always mu equals 0, unless the problem says it is claimed that you will raise your score 100 points. Then your mu difference would be 100, okay? But if you're just trying to see if you did better or whatever, you set your null hypothesis to be mu equals 0. And then depending on the context of the problem, your HA will either be that that it was different than 0, that there is a difference, or for example, if you're taking a SAT prep course and you took the SAT, you take this course and then you take it again, that company's alternative probably is that you're going to do better. So you would say mu is greater than 0. You're going to make an improvement. The change will be greater than 0. Okay. You always need to put the direction of your change when you're subtracting. If you're doing after minus before, be sure to do that, because if you do before minus after, then you'll get negative values, and so you need to keep track of the direction of your difference. Okay, you'll try that, and I will certainly answer questions from that during our conference time when you get to the homework question that has you doing that. I can tell you that on Chapter 12 test, you have one of these. It's like they do a course, you take a test, do a course, take a test again, and you want to see if there's a difference. So make sure that you practice a paired t-test. Notice I'm not calling it a one sample t. It's not called a one sample t. It's called a paired t. So far we've learned 3 different tests. We've learned the one sample z test in chapter 11. Now the one sample t test here and the paired t test. So we would need to identify it. And then Soon we'll be doing the one sample proportion, and then we'll get to two sample means and proportions. Okay. All right. Now, what I want you to do is pull out that worksheet that came along with this lesson. If you need to pause me and go print it for yourself or pull it up, do so. Okay. If you're back from getting it, here is the problem. Okay. You've got a one sample t-test I'd like you to do here. You've given some data, 12 items, so you need to do state, plan, do, conclude. Put this into your calculator, run one of our stats, and also do your sketch and come back and I'll show you the answer key for this one. Okay. Oops. Of course, I don't have it up here. Why not? This is draw. I could pause all this. I need to pause. Can't pause. Sorry about this, guys. Come on. I had it open. It must have disappeared on me. So here we go. All right. Sorry about all that. You've got your state. We want to test a claim about the true mean number of minutes of music every hour. What do I have there? It's a mu. Do I mean? Yeah, the true mean. At a classic rock radio station, at the alpha is 0.05 level. There's your ho, and your ha is that it's less than 50. Okay. So here's your conditions and your procedure. It's a one sample t-test. Your SRS was given. 12 is less than 30, but I just, whatever plot you did, you can see it's fairly symmetrical, fairly linear. It's got a little bit of a glitch there, but there's no outliers. I went and did this because these didn't tell me. I had some problems with that, but I looked and saw that there's not any outliers. So we're going to go ahead and proceed. Okay. And then the 10N is up here, so it's independent. Here's your one bar stats. Your T statistic was negative 2.56. Well, I guess I forgot to tell you, when you get a negative T value, you need to go use the positive value on the T table, okay, and find it between there. So DF was 11, and you go find the absolute value of that fell between 2.328 and 2.718. Following that up was 0.01 to 0.02. I did not multiply this one by 2 because this was a one-tailed test. So your p-value is between 0.1 and 0.02. You can also run, once you get your t, you can run this TCDF in the calculator. 100 standard deviations away is pretty close to infinity. Up to your t value will be your upper here, because I'm going from a negative a negative side to the negative t for a DF of 11. And you can see here it gives you a p-value 0.01326. That is definitely between these two, but it just gives you a more exact value. If you had a positive t, then you would put the positive t here as your lower, and then 100 for the upper to go to the right side, and then your DF, and you'll get a p-value. So that's just one way to get an exact p-value. But for us from the table, since p is less than 0.02, for sure, we know it's 0.01326, that is less than 0.05. We do have statistically significant evidence to reject HO and accept the HA as likely. So it's likely the radio station is playing less music per hour than the 50 minutes that they claimed. Okay, so let's go back now to this worksheet, and you have the back side with an additional problem. And I really do want you to try this because with the COVID test, you're going to be probably given mini tab information. So here's your mini tab. This is children playing a game, Don't Break the Ice, and they give you the data already here, and it asks you to interpret the standard deviation, okay, where you can see that's here. S3 is the standard deviation versus the standard error, which is S4. Now remember, standard deviation is of your sample. So that's the sample standard deviation. But the standard error is when you take that standard deviation divided by square root of n to get your sampling error for your margin of error that we've been using. Okay, that's the sampling error of the sampling distribution. Now, not just one sample, but a distribution of such samples. Okay, so it asks you to compare those and then tell me if that gives us convincing evidence or not. Use the data here and see if you can figure that out, and go to Edpuzzle and put it in and come back here and I will show you. Okay, so as I was saying before, this is your, I showed you the two parts, that this is the spread of the sample, whereas your standard error is the spread of the sampling distribution of many samples of size 50. Okay, so we got a ho and a ha here. It's a two-tailed test. When you run your test statistic, I got negative 0.95322 with a DF of 49. Okay, so I went to the table and saw that it falls. Remember, you take the absolute value of that to find it on the table. Falls between these two, which follows up to 0.15 to 0.20, but it's two-tailed, so we're going to times that by 2 and say that our p-value is between 0.3 and 0.4. Dear God, that's pretty high. So we know that we are going to fail to reject the Ho and assume that their claim is okay, which means in context that machine seems to be doing the job correctly. Of course, you need all your conditions. They were all met as well. I just did a quick one there for you to see how to get data from a mini tab and how to read that. Really highlight this because, like I said, with the COVID, they've said that they're going to not require calculators to be used. Instead, they'll be giving you information like this, and it's really important that you know how to read it. All right, this was long. The rest of the chapter is a lot easier, but hopefully the work itself is not too confusing. Tomorrow in notes or in conference time, I'll be sure to help you go through reading the table. And like I said, tomorrow's notes will get out the calculators. Okay. All right. Have fun practicing with it, and I'll see you guys tomorrow.